Welcome to Data Science 1, Probability, Discrete Distribution Summary. Okay, some items to remember are the Bernoulli Distribution, the Binomial Distribution, the Poisson Distribution, the Geometric Distribution, and the Negative Binomial Distribution, as well as expectations. What we're going to do is do a quick review over all of these before we move on to continuous distributions. All right, so the Bernoulli Distribution. Remember, it's a Bernoulli trial, has two outcomes, S and F. We'll call them success and failure. The outcomes are not ambiguous. It's one or the other, and it must be one or the other. The trial, when it's conducted, one of the two outcomes will happen. Okay, the probability space is of this probability of S, our success, is in the interval from 0 to 1, and that's all I'm going to say about it. Here, the random variable is 0 or 1. It's 1 if it's an S. It's 0 otherwise. We have a probability distribution, and I wrote it in a weird way down here just to show you a different way of writing it. Notice that when x is equal to 1, this piece is p, but this piece here is 0, so we don't worry about that. When x is 0, this is 0, this is 1, and then we end up with 1 minus p there. So it's just a different way of writing it. The mean and the variance are mu is equal to p, and the variance is p times 1 minus p. We didn't actually go over this, and some of these distributions we didn't go over these, but I'm giving you the information anyway because some of these might be exercises that you want to work through. Okay, so the binomial distribution is just saying I'd like to do more of those Bernoulli trials. Okay, you're going to do n of them, and you know how many you're going to do ahead of time. So you're going to plan them out and say I'm going to do 20 of them, and each trial is going to be independent of the others, meaning that the outcome of one doesn't influence the outcome of the other, doesn't change any probabilities. The probability of S is in the interval from 0 to 1, and it's the same for each trial. It's not going to vary across the trials. Here, our random variable is equal to the number of successes from the n trials. So we're just going to count them up. Okay, the probability distribution is the one we've seen before. Notice it has 0 in its domain here. Just forget that you could get 0 successes. The mean is n times p, and the variance is n times p times 1 minus p. All right, the geometric distribution. So each trial is going to be a Bernoulli trial. Each trial is independent from the others. The probability of success is the same for each trial, and the experiment terminates when it terminates at the first success. So as soon as we see a success, we quit. Okay, so X is the number of failures before the first success. And the probability distribution is given by this, which we've seen before. I didn't actually show you what the mean or the variance was before. I think I just told you what they were. Maybe I told you what the mean was. But it's 1 minus p over p for the mean and 1 minus p over p squared for the variance. Negative binomial distribution. We really didn't talk about this one too much on purpose because it's a little more exotic, but it is an extension of the geometric distribution. Okay, so again, we have Bernoulli trials. Each trial is independent of the other one. The probability is the same for each trial, and the experiment terminates after the rth success. Okay, so we're going to have r successes, and that's when we're going to stop. So maybe I just pick that to be 5. I'll keep going until I get 5 successes. So the probability distribution for this is given by this, and this is why it's called the negative binomial distribution, because it kind of looks more like the binomial distribution than the geometric, but it really is more like a geometric experiment. The mean here is r times 1 minus p over p. And the variance is r times 1 minus p over p squared. All right, and we're rounding this out with the Poisson distribution. So the Poisson distribution has a specified interval of space-time. We're going to observe Bernoulli outcomes during that space-time interval. The Bernoulli outcomes are independent of each other. We're going to assume that. So x is the number of Bernoulli outcomes that we see over the space-time interval. So whenever I hear a count over time, I'm thinking it's probably Poisson or something like that. It has a parameter lambda, which happens to be its mean and its variance. So that's kind of unique and interesting to think about. They have exactly the same mean and the same variance, which is easy to calculate if you know the number. All right, so there are lots of other distributions we did not cover. But what I'm trying to get across is it's extremely important for you to know the experiment that generates your data. Okay, a lot of people don't know this. They just assume that it comes from something. Okay, know what the mechanism that it generated your data is, because that will help your analysis later when you do the statistics side of things. It's important to make sure that your assumptions are valid for your experiments, and a lot of times they're not. For example, if you're doing something where the one will influence another, like independence. So if I'm asking a question that's yes or no, that's a Bernoulli outcome, and two people are standing next to each other and they hear one person say yes, then the other person might be more likely to say yes. So the probability did change across those. Now, these are theoretical calculations, okay? This basically is what we would expect would happen in the population because we've considered every possible outcome. And it gives us a bridge to inference because we'll be able to take our theoretical calculations and compare them to what we actually observed in the real world. And this is the beginning of building this bridge that we're going to be spending a little bit of time doing after we talk about continuous distributions. Okay, now remember, this represents the population. All possible outcomes were considered. Now, if you go and do sampling, you don't get every possible outcome, because you can only have so many samples that you can take. All right, so we're going to change gears here, and we're going to move on to continuous distributions. Now, the continuous distribution portion will have some calculus in it, but I'm going to make sure that it's not too painful, in the sense that I'm going to give you the answer that you'll need to move forward for most of you. If you know calculus, then by all means, work through the calculations, make sure you know how to do them. But if you're not that familiar with calculus, don't worry. You will see it because you need to know it exists and that it is holding all of this together. But it's not going to be so painful that you won't be able to figure out what's going on, okay? So we'll see you there.